Welcome back to the last session of the afternoon. You've had a really rich day of information. I am truly surprised to see so many people still here. We don't normally have such a crowd at this point because we're down to the last section, which is what do you have to work with? We know that this rich day leads to a lot of thought and action on your intended action on your part. What do you have to work with? We'll show you some of the shared research assets we have. There is a thing we call, there's a centroid of things that we call the commons strategy, the commons not platform, the commons assets. And those assets are actually were born out of what was called the information commons, defined about 7 years ago. Now, the commons are a joint effort of the Baker Institute, CRIO's office, CTSI, IT's ARS organization in particular, and more, and the other ones that support the product, the library and departments of neurology and radiology, 7 years and counting. We think of these assets in 4 layers. Compliant, you can read them. There's a word called knowledge bases. I'm going to come back to that, but those are the layers. There's another layer on top called integration, which has an enormous benefit. It just isn't on this slide. You'll see it soon. But there's some real meaning behind that. Now, if you look at, there are 3 large entities across the university that actually have assets that are relevant across these 4 horizontal layers. We're not going to talk so much about what might be the largest one, which is our PI and organizational assets. When I say organizational, that means departments that have lots of pathology data or radiology even and so on. But we're not talking of that. We're talking of the big middle. But before that, one of the critically important areas is how do we put research models in clinical deployment and tests. We had some education this morning from the opening speakers on sort of the AI governance oversight. AER and HIPAC were mentioned. Hossein Soleimani, Sarah Murray, those are the folks who take care of that side. Nothing more to say about that over here, except that's one of our critically valuable assets. But we're going to talk about the middle, which is the shared institutional research assets. Now, this is the previous diagram in a slightly fuller form. Slide 5, so I should be reading that. First, let me take it from top to the bottom. The one that I think really sets us apart is the integration layer, because you really get training, documentation, sample code with linkages, support, all of the stuff that you get from our ARS organization. That's our key over here. In the next slide, we'll talk about the principles. Now, the next layer, tools and models, that's where a lot of the action is, and you'll be hearing from different speakers. As the chancellor himself said, we're going from genes all the way to the right-hand side. And very roughly, I've laid out these from genes through proteins, through PG pharmacogenomics and so on, onto the clinical sciences. And all the way to the right, I've emphasized this word called reasoning. Reasoning, as they think in the AI world, there are 3 legs to intelligence: AI itself, knowledge bases, and reasoning. That's when you get to intelligence. And so the world is on the lookout for defining those. That's why reasoning appears over there. Software libraries in support of the above. Down, let's jump one layer and come to the data and knowledge bases. Knowledge bases are what do you know which is scientifically accepted. You actually know about 1 trillion different elements of what is associated with what gene with disease, or protein, or I should say pathway with inflammation pathway with disease. You know about 1 billion or 1 trillion things. I don't know the number, but either you can ask Sergio or who cares, because it's so large. That's knowledge, as opposed to data, which is that which you observed, even with a patient or in a lab. Knowledge bases are becoming extremely important to advance intelligence. You sort of got the hint all day long when they were talking about LLMs taking you this far and then beyond that. And then down into a fully compliant infrastructure. Then you've got something called programmatic metadata. That's a little bit arcane as it stands as over there. But one of the things that's really important for us is to start using our Spoke knowledge network and use it for metadata along with other things that we're doing. What are the principles? The principles are, these have become our differentiators. Everything fully linked. Programmatically searchable in real time, fully linked. Self-service, you don't have to go get a consultation if you are able to self-serve. Built to scale. Built to scale means scale up to the sorts of numbers you saw today. Now, that doesn't mean you go 10 to the 80 like Jamie Fraser showed, that you have to simplify the problem somewhere. But everything fully linked makes it really much easier to start and build to scale as you go towards a sort of angstrom level on the left-hand side. No further IRB. That happens to have been a phenomenal, unique differentiator. Everything is de-identified, including all our clinical data that we do have. You don't need a further IRB unless you want certain specific things like geography of patients. I'll jump to the last one. There are two tiers of what we have as products over here. One is a product, which is tier one, top level, established. Yes, we need to support this. And then there's a more emerging sorts of stuff, which is under evaluation. That's tier two. You'll see some of that. Lastly, let me talk about a few things that are going to be shown by our next few speakers. We saw many multimodal studies on top, but protein language models. Jimmy Yee, for those that attended that, and Gundolf Schenk will talk about protein language models. What expression can you express? Can you expect from proteins given a certain SNP or profile? Then Yun Song will take it a league beyond by actually doing GPN, which takes on the fuller complexity of the human genome and the predictions for deleted and SS. I don't know how to pronounce these 10-syllable words, but you know what I'm saying. Gene Former, you heard from Christina today, that gets truly into the cellular levels. It looks into the cell and predicts chromatin dynamics simply from transcriptomic data. So now you're getting towards the middle of the diagram. Causal inferencing, it's a vital field to support reasoning. You heard this morning from Mark Fletcher about how it applies in population studies. But there are other forms of inferencing, abductive, inductive, deductive. Those don't go as far as causal inferencing. That's vitally important. Okay, Spoke is a fundamental thing that Gundolf will speak about. It's the knowledge graph we've got, much more to come. And last thing I'll say is this Versa. Versa is our LLM chats. I guess two things. Versa is our LLM chats. That's a whole platform. And there's more to Versa than chats. There's also the API and all that stuff. But looking from top down, Versa is our platform. Lastly, there's a clinical notes foundation model across all of the UCSF notes now, all 180 million of them. And that's called UCSF GPT. That's something more we're introducing over here. With that said, there'll be a lot of detail in the poster session. Let me just introduce the first speaker who will speak about certain models. I only have one ground rule request. When and if you get to ask questions, please keep your questions brief so we can get as many questions in as possible. With that said, Dr. Yun Song, he's professor of computer sciences and statistics at Berkeley. I could tell you about the speakers' awards. You could listen to those or you could listen to the speakers. He's got many awards. The only two I'll say is a Chan Zuckerberg BioHub Investigator and NSF Career Award, and several at MIT, at Stanford, where he got his math and physics degrees.
Okay, well, thank you for the invitation. So today I want to tell you about some work that's been done in my lab. So as you all know, natural language processing has undergone transformative changes in the past 5 to 7 years. And there has been intense interest in adapting these techniques to biological sequences, DNA, RNAs, and proteins. And my lab has been actively involved in this development of the past 5 years. So our interest is really driven by interesting applications. including predicting the effect of mutation in the genome, contributing to disease risk or other traits. Sometimes we want to design new molecules such as proteins, RNAs, and regulatory elements. So what I want to do today is to showcase a couple of examples. So I will first start with proteins and then go to discuss genome-wide predictions. So as you probably know, there are now a number of models called protein language models that are really effective in predicting variant effects, protein structures, even for design. But these models are really learning about probability distributions of protein sequences that are observed today in databases. And these models are not really able to model how a protein sequence evolves over time, experiencing mutations, selections, and adapting new function. So what we aim to do in my lab is to not just think about deep models of protein sequences, but deep models of protein evolution. So what we want to do is to train a model that can learn how a sequence X evolves to another sequence Y, which may be of different length in a given amount of time. And we do this by leveraging deep neural networks. So our model is called Protein Evolution in Time. It's called PAINT, and is a degenerative model. It does not even need alignment to train the model, and it actually generalizes to unseen protein families. So given this model, what we can do is to simulate evolution forward in time if you are given a tree. You start from the root sequence and you propagate downward to generate sequences at the leaves. And we can actually show that the protein sequences that we can generate are highly structured, confident structures. And also they actually have conservation patterns at, for example, at important sites, such as those sites involved in catalytic activities. So I'm not going to show you in this talk about the benchmarking results that we have done, but I want to actually take one application that we have undertaken, which is experimental validation, synthesizing a de novo enzyme. So can our model actually generate novel functional proteins? So to answer this question, we looked at enzyme called carbonic anhydrase, which is really important for carbon dioxide fixation. So it's really important for climate control. And what we have done is to take an existing enzyme, a beta carbonic anhydrase, which is a homodimer, and we tried to simulate evolution on the tree as shown on figure A. And the sequences we get at the leaves are quite divergent from the original sequence. So we got at most 45% identical to any known sequences actually in the database, not only to the root sequence, but for all known protein sequences. So these are really novel protein sequences. And furthermore, our proteins actually can conserve those active sites. So these are actually not forced by hand, but these are actually coming from the model. So active sites actually conserve as shown in figure B. So we actually tried to look for test for functionality. So we did some complementation assay using E. coli. And we were very happy to see that the hit rate for the enzyme is actually quite high. 5 out of 20 actually are functional. So I want to emphasize that this is really extremely high hit rate. So if you have read the papers from David Baker's lab, so first round hit rate for proteins synthesized by the Baker lab is like 1 in 1,000. So in fact, the luciferase paper from, I think, Nature of Science had a hit rate of 3 out of 7,000. So 5 out of 20 actually seems pretty good. So I want to emphasize that this is not just a model, it's a framework, and we can apply to tackle many different problems. So we are thinking about extending the framework to incorporate structure, so we can actually jointly model sequence and structure, and we can think about generating sequences conditioned on a given structure. We can also handle multiple subunits. So suppose I have a multi-subunit protein complex, and we can also handle that. And we are working on that. We can also model antibody evolution. After all, affinity maturation is an evolutionary process, and we can actually train our model on affinity maturation process. And you can use it to engineer new antibodies. We can also apply to RNAs and DNAs and predict viral evolution and many other applications. So I want to now move on to DNA. So what can we do with DNAs? So it turns out that training a language model for DNA is actually much more challenging problem. So we actually we actually have a new review paper in Trends in Genetics describing the opportunities and challenges. I will refer you to the paper, but I just want to mention that this is actually not an easy problem. And the main challenge really comes from two facts, I think. The first thing is that unlike in protein, where you already have a functional unit that is a protein itself, when you have a genome, we don't really know where the functional elements are. So functional elements in the genome are completely overshadowed by amounts of non-functional elements. So really, it's really hard for the model to learn where the functional elements in the genome. Secondly, unlike protein sequences where we have hundreds of millions, we don't actually have that many whole genome sequences. In order for the model to learn, for example, regulatory elements, we need to have whole genome sequences, but they are not really available. And we don't know how to find them, even if we have the genomes. So, is the scale the solution to this problem? The larger, the better? I don't know. Some people believe that that's the answer. And indeed, companies like NVIDIA has trained a model called the nucleotide transformer model, has 2.5 billion parameters. It took them 1 month, 128 GPUs. And recently, the Arc Institute published this paper, preprint EVO2 has 40 billion parameters, and they used 2022 GPUs and took several months. And this actually received a news coverage by Nature for being the biggest AI model for biology out there. But is it really doing useful things? It's a great engineering achievement, and I give them a lot of credit for their work. But as a community, we need to really be thinking about what actually they have learned. So, I come from Berkeley. UCSF is richer than Berkeley, and we don't have this kind of resources at Berkeley. We are a poor public university. And so I tell my students, there's no way I can actually even afford like 22 GPUs. So I actually included 22, although you may think it's not a significant number. It is actually very significant to us. We cannot even afford 22 GPUs. So I tell my students, rather than trying to rely on GPUs, maybe we should be utilizing BPUs, brain processing unit, which is almost free, but it's actually could be more powerful. So we actually did that, and our model is called GPN MSA, and we only needed 4 GPUs, and it takes 3 hours to train rather than days or months to train. Much smaller model. So I would argue that actually our model actually is quite useful. And the reason why we were able to develop such a good model is because it's actually fast to train. We can iterate on ideas. We have some good ideas, some are not as good ideas, but we need to try them out and we have good intuition. But if we need to wait 7 months to train a model using 2,000 GPUs, there's no way we can do any development. So what we are able to do is in fact, the key idea is to integrate AI with biology. So we call it inductive bias. Rather than let the model figure out what it's supposed to learn, what we hope that it would learn, we try to guide the learning by providing biological insight and knowledge. And the knowledge is coming from evolution. So here we are using vertebrate genomes. So rather than just using contextual information across the genome, we provide information about evolution. That is, the column in this MSA is telling you about evolutionary process, conservation patterns. And this was actually quite essential for the model to learn what's actually important or not. So this is just one benchmark. Please read our paper if you would like to look at more details. So here are some regulatory variant effect prediction, probably the most challenging variant effect prediction problem. And we are definitely much better than any models that we have benchmark against, including the nucleotide transformer model I alluded to. So higher the better in this case. So we looked at promoter variants, enhancers, non-coding RNAs, and UTRs. So what can we do with this model? We think the real utility of the model is actually rare variant association testing. We think that we can improve rare variant association testing, and we are collaborating with the team that actually have developed our DVAR-VET, published in Nature Genetics last year. So this plot is showing that by incorporating GP and MSA scores into rare variant association testing, we can actually boost the power of detection. So does scaling help? So we actually try to look at EVO2 since it actually has received so much attention. And well, the take-home message is that scaling does help. If you go from 1 billion to 40 billion, the performance increases, but yet it actually does not really reach the level that we can achieve by using inductive bias from evolution, alignment-based models. So another key message here I want to convey is that although EVO2 is actually working pretty well for promoter regions and UTRs and non-coding RNAs, it really does not perform very well on enhancers. So the key takeaway is that scaling is really important, but it has to be coupled with the right data curation. So we think that deep models of probabilistic probabilistic models for biological sequences actually has really high potential. For example, for predicting disease risk, learning about gene regulation, for designing novel molecules. But there's a lot to be done in this field. So I want to end by saying that I collaborate a lot with UCSF. I'm here today because actually I want to reach out to the community and let you know that we are open to collaboration. So if you're interested in collaborating, please do reach out. And I want to end by thanking the students and the postdocs involved. Thank you.
Thank you. This is a beautiful work. Just out of curiosity, when you sort of talk about the, finding the final probabilities, looking at the evolutionary tree, and you talked about a little bit of scaling that we don't have to sort of scale too much. Is there a relation between the length of the tree versus the scaling time, or is it like it's a general phenomena that you have observed, which is, let's say, the evolutionary tree agnostic? Because from the principles, we know that a system tends to sort of get to that steady state quite well when we sort of traverse through that evolutionary trajectory.
So I'm not so sure whether I completely understand the question here. So what we believe is that different evolutionary timescales capture different information. And this is actually very important to distinguish. Some things actually may be better if you use only primates. And some information may be better if you actually look at much longer time scale. And so I don't know whether that's...
No, that's on track, yeah.
And I want to also mention that the context size may not matter as much as what kind of inductive bias you introduce. Some people think that the larger the better. Some models actually have 1 million base context size, and I don't think it's really necessary for learning something about functional consequence of a mutation deleteriousness. It's much more important when you want to learn about gene regulation. So when people talk about foundation model, I really don't like it because I don't think there's such one. It really depends on the application you have in mind.
Got it. Thank you.
Just naive question. Are your models able to like integrate with each other, your DNA and the protein models?
So that's a good question. So I think protein models are much better at missense mutation predictions, that's for sure. But again, it depends on the time scale. If you're interested in predicting the effect of mutation on cancer, I don't think protein language models are necessarily the best one. In fact, we actually have shown in our paper that because of the training data, protein language models are trained on evolution that has happened over billions of years. They may not be so relevant for cancer biology. You may actually want to train a model that's more relevant to human biology, and that maybe we actually have shown that DNA language model is more powerful for that. Thank you.
GP and MSA is available in his lab's Git. we will bring it in as one of our emerging models and give it a whirl. Dr. Maya Petersen is professor of biostatistics and epidemiology at UC Berkeley. Her methodological research is on novel causal inferencing in health. She's the founding editor of Journal of Causal Inferencing, and she's on the editorial board of epidemiology. Her degrees and training are from Stanford, Berkeley, and the Howard Hughes Medical Institute. She is co-director of the Computational Precision Health Joint Program with UCSF. Now, that was my short introduction, but I was given a much longer introduction, of which I'll just take one sentence, the last one. I didn't author this. In 2021, Mayor London Breed named June 18th, coming up, as Maya Petersen Day in San Francisco in acknowledgement of her services to the COVID pandemic response. Welcome.
Thanks so much, Sharat. And thank you to the organizers for having me at this wonderful event. Let's get the... I'm going to be talking about what might generally be, there we go, generally be termed causal AI and the use of causal AI to advance clinical care. And in particular, I'm going to talk about some very recent and ongoing work I'm excited about in deep causal behavioral policy learning. This is joint work with Jonas Knecht, as well as John Kolstad and Anna Zink. So to start with, I'm going to take the basic premise that clinical knowledge is far too siloed and lacks care. So there's so much deep knowledge, but it's not efficiently reaching all the pieces and people and places and patients that it needs to. We have language, but language, whether it's textbooks, guidelines, publications, or even clinical notes, encodes only a small portion of that expertise. So what we're stuck with is a situation where some of the most valuable knowledge that humans have ever produced exists only in the actions of real-world skilled providers. And current AI approaches, even some of these incredible advances in large language models, are not currently designed to efficiently encode that knowledge so that we can use it to improve care. So I'll just give a quick example. So I think we're all familiar with AI scribes. They can record a patient encounter, generate a draft note, and then the provider can edit it, make changes, and there are huge potential upsides to this technology. So reduce workload, reduce burnout, potential to improve interactions. There are also lots of well-recognized potential shortcomings or limitations, hallucinations. The LLM doesn't always know what it doesn't know. What I'd like to talk about now, though, is kind of a more fundamental limitation. We may be asking this scribe to do a different task than it's going to end up doing. So right now, it generates a draft note. It's very easy for the scope of that task to increase. So all of a sudden, it may be not generating a draft note. It may actually be suggesting a next clinical action, a prescriptive action, a diagnostic image. And that is a very different task. So to oversimplify in the name of time, asking what word usually comes next in text is really a fundamentally different task than asking which clinical action usually or most likely comes next in time. So I would say today that what we need is really a new approach to health AI to be able to unlock some of that knowledge. So all of this rich clinical knowledge is encoded in actions, and we're fortunate because medicine is fairly unique in the amount of digital information that we record on our actions over time. So we're taking this new approach, and it's really based on a fundamental insight from behavioral economics that human behavior is a great way to encode and reveal very complex knowledge and decision-making processes. So in this case, we have expert clinical judgment being executed every day and being revealed in the actions captured in the electronic medical records. So what we're doing is training what we call a large clinical behavioral model. It treats this as a sequence-to-sequence task and uses a transformer architecture to learn to predict the next clinical action given a rich patient context and, importantly, the timing of that context. So I'll give you a flavor of what this looks like. So here's an example of some of the data that's used to train these models. So we have a patient that presents to the ED, a woman with chest pain, 70 years old. Over time, of course, we follow that patient. We record orders that are placed, including a number of initial exams and tests, diagnostic tests, as well as imaging. And then follow the patient over time. We record the results of those tests, and then finally we record a diagnosis or an outcome. So what does the large clinical behavioral model do with this kind of information? So at each time point, it's taking as input this rich clinical context, and it's giving as output next predicted clinical action. So if we follow this patient along, we see something kind of interesting happen. They're coming in and they're getting a typical MI workup. But then all of a sudden, a CT of the brain is ordered. So before it saw that CT, the large clinical behavioral model didn't think that was very likely. It gave it a 22% probability. But once that happened, it was able to pick up that that was a pivotal order, a pivotal action, and use that information to then go on to predict a totally different diagnostic trajectory based on cerebral hemorrhage. And that ended up being what this patient had. So just for comparison, what happens when you give that to just sort of a more off-the-shelf LLM-based approach? It ends up being unable to pick up that rich, important temporal and action context, and instead just kind of loops over the classic MI workup. So large clinical behavioral models give us a way of moving beyond LLMs, what word usually comes next, to asking what clinical actions are likely to come next in time. And that's already a huge advance. It opens up all sorts of potential applications. But I want to focus on one in particular. So what do we make of these unexpected clinical actions? So in this case, this CT of the brain. Is it optimal care? Is it actually this pivotal action that correctly sends us off down a new important diagnostic pathway? Or is it an anomaly or somehow suboptimal care? Even a large clinical behavioral model alone can't answer that. So that then brings us to the role of causal modeling and really the power of combining formal causal inference methods with this large clinical behavioral model. So we're now going to go from asking which clinical actions are likely to come next in time to a much more, in some ways, interesting and impactful question, which clinical actions should come next? And this allows us to start doing things like develop and evaluate personalized optimal care strategies over time and quantify the potential impacts of those strategies. So I'm going to spend the rest of my time just giving a little overview of how we're approaching this. So the first thing is that we need a formal causal model. So what this does is it really, in some ways, describes what we know and what we don't know about the process of delivering clinical care. So in a highly abstracted form on this slide, you could think of what is it that clinical care is. It means taking in this complex patient information, deciding on a clinical action or multiple actions. Those actions then change future patient states as well as reveal more information, and the process continues over time. And what we'd really like to do is optimize that complex longitudinal decision-making process to optimize outcomes over the long term. And you might call this longitudinal algorithmic decision-making process that clinicians are doing all the time a clinical behavioral policy. So how do we learn about the effects of these behavioral policies? You might think you could do something as simple as just match patients who got different care and compare their outcomes. Actually, it turns out that doesn't work well in a lot of cases. There's simple cases where it does, but a lot of times it doesn't. And the core challenge there is really unmeasured confounding. So in essence, for example, patients who get a diagnostic test may be higher risk and in ways we simply didn't record. So this brings us to our approach, which we call deep causal behavioral policy learning. It consists of 3 basic steps. First, we learn a personalized match of patients to skilled providers. So basically, at this first step, we're asking for a patient like this, which hypothetical provider assignment would have had the best outcomes? Second, we model provider-specific clinical practice, and this is where our large clinical behavioral model comes in. So next, we move to asking for a patient like this, which actions or action policies over time would these skilled providers have provided to this patient? And then third, we quantify the causal impacts of these different practice patterns. So how much would outcomes have differed under some of these different policies or ways of delivering care? So I'll just take a minute and say a few words about each of these steps. So with this first step, how are we doing this? The fundamental, I would say, assumption that we're relying on here is that unmeasured confounding is a profound problem at the level of individual actions, but it's a more tractable problem at the level of providers. So what we're doing is leveraging quasi-randomness in provider assignment, such as we get from, say, shift changes. Now, of course, provider assignment is not at all completely random. So we also bring in the latest in causal machine learning approaches to allow us to flexibly adjust for all the rich multimodal patient data that will allow us to essentially balance out the different types of patients and contexts that different providers encounter. The second thing we use causal machine learning methods for at this stage is really to do this personalized matching. So we're not asking which providers have the best outcomes overall. We're asking which providers would have the best outcomes for this type of patient. So once we've done that, we then move on to identifying these, modeling these provider-specific clinical practices or behavioral policies. And here again, we use our large clinical behavioral model. So we use our pre-trained model that I showed you an example of before, but then we fine-tune it to the clinical practice of specific providers. And then finally, we move to this final stage of really quantifying the causal impacts of these different practice patterns. And here again, we're making use of causal machine learning or causal AI methods. The core assumption at this stage is that providers affect outcomes predominantly through their recorded clinical actions. And this is an assumption that's going to become more and more tractable, I think, as the richness of what we're capturing in electronic medical records increases. So where are we at and what's the next step? So I've done a proof of concept of this using UCSF Information Commons, and thank you very much. The basics are that we see what we expect, that accuracy is improving with scale and context, that using uncertainty quantification lets us reduce errors. And in this simplified task and performance metrics, we do see better performance than off-the-shelf LLMs. But again, this is a simplified task on a limited sample size, about 180 encounters. So right now, what we're doing is training at scale. So this is a research partnership with Providence Health at a much larger scale. And then obviously there's a lot of methodological details that I've rushed over in the course of a 10-minute talk. And so really diving into a lot of those, both on the LCBM side and the causal side. So to conclude, we are really building out what I think is a new approach to AI in healthcare. I think quite complementary to some of the talks we heard earlier, including Dr. Ritchie's, making full use of efficiently encoding clinical action paths or the language of medicine in its full temporal context, and then using causal inference to learn complete sequence-to-sequence models of how a particular optimal doctor or provider would treat a patient. And there are broad applications of this in healthcare, so beyond from understanding practice patterns to quality improvement to real-time clinical decision support, and ultimately the goal of de-siloing and scaling clinical expertise. So to conclude, just want to acknowledge again my co-authors, and Jonas is the first author on this work, and he has a fantastic poster if you want to dive into the details of both the engineering or some of the performance metrics, so go see it. And we also have a new paper up on arXiv. Thanks.
Thanks, Maya. It's really exciting to see this work. My question is about like the concept of an action and where those come from. And I think in your examples, it mostly looked like testing and maybe medications. And so like, how would an action like watchful waiting, like, does that show up? And maybe as part of that, like, how are you using notes? Because whether notes capture actions, I think is sort of a tenuous question.
Absolutely. So a series of answers to that question. I think the example I showed was like was kind of a simplified version of actions. They were mainly tests. I think as we move out, you also can think of consults, all sorts of other types of orders that would be captured immediately in the EHR. And then, yes, absolutely. I think ultimately we want to go to the broader set of clinical actions, which will require extraction from notes. So I think all feasible, probably not all feasible tomorrow, but all kind of within this roadmap or pathway, and very excited about seeing where that goes.
So, hello everyone. My name is Gundolf Schenk. I work for the Baker Computational Health Science Institute, and I'm gonna tell you a little bit of the tools and models that you can use today in information commons and adjacent technologies. So it might look a little bit that I will be jumping back and forth a little bit, but the theme is I'm going to start at clinical data, clinical notes, what you can do with that, and what we've done to help you look into the information that's buried in clinical notes. Then going to cancer, and then further on, some general tools that will remind you maybe of some of Tony Capra's slides, if you remember the multi-scale. I'm going to come back to that. And then I will close out with some biological reference data. So going all the way from clinical to molecular data. So let's see how this works. Okay, so natural language processing is useful, has been around for a couple of decades now, and we know that there are LLMs out there. I'm going to show you how useful traditional approaches are that are rules-based, but also how machine learning and AI-based approaches can be. So what we've done at UCSF, we've collected all the clinical notes and the reports that you can find in the EHR, and then we de-identified them with a certified, approved de-identifying algorithm that's called filter. And then we have used all those 180 million notes that we have today in information commons to extract concepts, biomedical concepts like symptoms, medications, diagnoses, labs, etc. And I'm listing there 3 different technologies. Apache CTEX is a rules-based technology. It's been around for 20 years or so. Tumor pathology and social determinants are in-house developments that are based on concurrent neural networks, so an AI-based approach. And furthermore, also in-house developed is a BERT model, which is also a transformer model developed by Madhumita Sushil to do various different tasks trained on these clinical notes. And here it gives you a flavor of what can be extracted. Just using the rules-based approach, as I said, you can see all these different kinds of concepts along with certain attributes, like was this a history of, or was this a particular mention of hemoptysis was negated or not? Is there constipation, yes or no? And if there is a check mark, it means it's not. So along these things with standardized nomenclature. So thanks goes to Lakshmi Radhakrishnan from the IT RS team for co-developing the filter algorithm to de-identify. And if you want to learn more about UCSF BERT, please talk to Madhumita Sushil. Furthermore, we have a more recent model, and Sharat mentioned this. This is a GPT-based model, also trained on our UCSF clinical notes. They are all de-identified, so you don't have to have an IRB. We can look at all of them simultaneously. So there are 57 billion tokens that you can extract from them, train a transformer model like GPT, and then have even a chat-like interface. If you want to learn more about that, talk to Rohit. He's somewhere back in the room. And yeah, with that, I'll move on to what else we have in information commons. It's the imaging commons. So radiology images use a de-identification algorithm as well. You can imagine there's, we've heard earlier today that the PHI may be burned into the images and so on. So they have developed, the CI2 Center for Intelligent Imaging has developed an algorithm to remove those and make this data available in the information commons without IRB. And there is a graphical interface that you can use. Go to this website. If you want to explore what the images are, there's like, you can display them and you can go through all the scans. Or of course, you can go and write your own Python or R Jupyter notebook. Yeah, and this is the data that we have today. extract it. It's a huge, complicated process that takes a lot of time because there's a lot of data. And if the data is not there yet, send an email to this website, to this email address, and it will get more. Moving on. Cancer Commons is built on top of the information, the electronic medical records that are de-identified in Information Commons. And we believe there are somewhere between tens of thousands of cancer patients. We don't know actually how many we really have, unless we really try to classify them. And so this is a poster that you can find downstairs. 59 is the number, 59. For Cancer Commons poster, trying to actually classify all our patients. First of all, find all the patients that have cancer at UCSF, and then classify them into what kind of cancer it is. And so this is like a triangle. You can get more and more specific in the type of cancer. We also have genomic testing, panel testing in Information Commons de-identified today. And you can look at it by going to this tool, cBioportal. It's run by the Molecular Oncology Initiative from the Cancer Center here at UCSF. And yeah, you can explore the data. You can filter by what kind of cancer type you're interested in or what kind of mutation you're interested in, and so on, and look at the statistics. You can even dive into individual patients. One of the themes that we heard earlier today, just before me, are protein language models. And one of the protein language models is ESM that came out of Meta AI. And Jimmy Yee talked about it today. And oops, there is the Vasilis Dranos labs as well that have created a tool based on this ESM model and to predict pathogenicity. We're helping at Becker Institute to turn that into a graphical user interface so that it becomes easier to use. Knowledge network. So what can we do with that? So we have all this translational, the foundational models, and we heard that they do some kind of hallucination sometimes, or not always correct, but they give a lot of correct results. But how do we know that we can actually do that? Maybe we should look into what we already know. So what do we know experimentally validated? So the experimental landscape is actually vast. We've seen the scales from molecular all the way to population. And in the Spoke knowledge network, you can find data at the bottom, which is, sort of the genotypes. And then even the simplest phenotype is expression of this data. And it can become more complicated if you look at the products of these genes, the proteins, and then how the proteins interact with each other in pathways, and how they form cellular processes, and so on, and until you get to the patient level and even population level, if you want. All of this is connected through known connections, through ontologies, through experiments, and you can go up and down this stack of complexity here. So the orders of magnitude, there are different ways to quantify it. I think of it as like, okay, if you go from nanometers to kilometers, that's like a huge amount of span that you have to go. And same in space, you go from nanoseconds to look at a chemical process all the way to maybe a couple of decades, 100 years perhaps, or longer. Yeah, so all of this comes from public databases and is interlinked with each other. So you can jump in any of these, this is the metagraph. So in any of these databases and node types, and go from one node type to the other. For example, if you start with a gene, maybe the gene is associated with a disease, and that the disease can be treated by a compound. That compound interacts with a protein, and so on. Okay. So in Spoke, please talk to Sergio. He's here in front of us, and there are a lot of different applications that you can use it for. I don't have time to go into all of this, but You can see working on EHR, drug discovery, large language models, social determinants of health, genetics, obviously, microbiome, even NASA is there, so there's some space applications, I suppose. So that's pretty cool. Talking about scale. So lastly, I'm going to talk about the bioinformatics repository, which is on Winton. You haven't heard of Winton yet, maybe? It's an on-premise high-performance computing cluster that you can use for data science or for bioinformatics, or just look at your files. But speaking of files, there are 45 unique databases, huge databases from consortia that include experimental data at various scales. They have been pre-downloaded for you, so you don't need to download it. You don't need to allocate space for it. You don't need to pay for the storage. And also 61 large paper-associated data sets. So they're mostly human functional genomics and metagenomics. But here is a flavor of maybe some of these ring a bell, like 1000 Genome or Ensemble, TCGA, some of you might have heard. Gene Expression Omnibus, AlphaFold we've heard several times already. And then on the compound level, there's obviously PubChem and Zinc and maybe ClinVar if you're interested. And this is not a complete list. I just picked a few that rang a bell to me. Okay, so with that, I'm gonna hand over to Rick Larson, who is gonna tell us about information commons and data and compute. Thank you.
Can you all hear me? So I asked Sharat on the side, what do you call the last speaker of the day, which is me, and I'm the keynote closing speaker. So don't tell my family, but I will go home and tell them I was a keynote speaker at this amazing event. So I work in IT. I'm in academic research services, and my area is research informatics. So it's an area I love, everything about data. My whole career has been about data. And it's great. The second half of my career has been around supporting data and tools and compute for the research community. I have 6 minutes to go through an hour's worth of materials. So I will move along. And the great news is most of what I'm covering is actually detailed on posters below with people that actually know much more than I do about the details of them. So please, if you want to learn any more about them, stop in those areas or grab me and I'll point you to the right person. So today I'm going to cover clinical data, tools, and compute environments that are associated with AI at UCSF. I am going to start with compute infrastructure at UCSF. And some key requirements that we need for compute is to support multimodal data, processing at scale, training and fine-tuning of models. This pyramid is an attempt to show kind of in a bottoms up the components for each. So you start with the base layer. Everything we do for institutional compute needs to cover the things that are on base. The interactive compute layer, that's really there to focus on the needs that you have when you're doing development, prototyping, and model testing at scale. Is there for when you're doing training, fine-tuning of models. And lastly, the deployment level is there to deploy models, either ones that you have downloaded or that you have actually developed. When I cover each component in each compute area, it will show at the bottom what is really that compute area is designed for, or that compute environment. I'm going to start with 3 environments that are here today, and then I'm going to talk about 3 that are coming quite soon. So first, research analysis environment, also known as RAY. To some of you that have been here a long time may still call it my research. RAY is, there is a RAY free and a RAY premium. The RAY free is basically equivalent to a powerful desktop environment. It has most of the normal analytics tools that you'd use, SAS, R, Stata. Those are all available to you. It has an information commons environment on it. So most of the data that's part of information commons can be accessible from Ray with those standard tools. And it also has a framework available on there to access Versa through Versa APIs. So a lot of people have actually, although Ray is not a huge environment, a lot of people have used Ray since we've been going to large language models to access Versa through API access. Gundolf talked a little bit about Winton. Winton is the high-performance computing environment that we've had for several years here at UCSF. It has over 1,500 users. It's historically supported large CPU jobs over the last several years. It's had more and more GPU-based jobs that are supported on it. It's a co-op model, and it's a combination of institutionally purchased compute as well as individual purchase compute. And actually, Gundolf gave the same example I am. One of the models that was developed on Winton is called UCSF GPT, and it was trained using de-identified nodes from Information Commons. It also hosts several locally hosted LLMs like Gemini and Llama. AWS Secure. This is a PHI safe environment that's hosted by UCSF IT. This is a place if you're doing AWS work you really want to be on because it's PHI compliant. It has negotiated rates so that you get a little bit better rates than you would if you were just go out to AWS. And it supports many, many different workloads in the AI world. The main, I guess, limiter on it is cost. So a lot of people can do a lot of things on AWS, but oftentimes the governor on it is the cost that can be run up. So now on to the future offerings, which I'm really excited to talk about. A couple of these have been in the works for over a year, and you've probably heard about some of them already, but I'm going to go through both the FAC or Facility for Advanced Computing, Core HPC, and then Information Commons FAC on Core HPC. So first of all, the Facility for Advanced Computing. It's actually going to be available in a few weeks. So early April, this will be available. FAC will be managed as far as system administration from the operating system down by IT admins, but end users are able to add their own applications, models to it and manage those themselves. It's a great option for users that need a scalable environment to do their modeling, development, prototyping, and actually deploy models on. And it will be supporting both VMs and purchased hardware and support GPU and CPU workloads. Core HPC next. It's being built from the ground up. So Winton was built up from the ground up initially for really supporting basic science use cases. Core HPC is being built from the ground up to support data science and AI use cases. It's a condo model, also has both institutional and individually purchased compute and storage. It actually shares the infrastructure with the FAC. So being able to move data around will be very seamless. Being able to Also deploy your executions, that things that you've done on FAC into and scale up to HPC will also be seamless. And it's really targeted to train and tune models, and it's targeted to be going live in June. And lastly, on the environments, we have ICFAC, so Information Commons FAC/Core HPC. And this is really taking the two environments I just talked about and putting the Information Commons infrastructure on it. So you have the data, the tools, and being able to go from across the FAC environment up and scale into HPC. So it's really that initial configuration that so many researchers have asked for, to really have a place to be able to go in and quickly doing the work and go all the way from development up through deployment. And it's being targeted to, this is the one least furthest along because we have the dependencies and we're working through processes, but we're hoping to start the work on that in early summer. And lastly, this is taking the information across all the environments and trying to show going left to right, kind of depending on what you want to do, what environment might be best for you. So it's, as you go left to right in general, to the right, it's supported more, but there's, depending on what you want to do, some of the systems on the left have what you would need. So I see a lot of people taking pictures of this one. This is my keeper, I guess. All right. Says I have 5 minutes left, but the clock says I'm out of time. So I'm going to go very quickly here. And the good news is I'm going to data and tools now. Much of what I would cover here, Gundolf has already done, so I can move a little bit quicker through this. So he actually covered that. And so I'm going to talk about structured EHR data. Gundolf talked about a lot of the great other data types we have today. I'll be talking specifically about the structured EHR data, both, I'm sorry, structured and unstructured clinical notes. So here you can quickly see a one slider of what data we have in the world of on Information Commons clinical data. You can see the types of patient counts we have, both on the health Epic side and the health, as well as SFDPH. One of the things we did very recently is at the end of last year, we added SFDPH Epic data to Information Commons. We use the Enterprise Master Patient Index to match patients. And you can see the intersection down at the bottom of the intersection of the percentage of SFDPH patients that are actually seen at UCSF. On the note side, you can see the number of notes, and a lot of the research has been done in AI in the last couple of years since LLMs have come along has been on notes, because the standard analytics tools, as you know, weren't that great for going through notes. On the tool side, here's some examples of the tools we support. We support the normal programming language for analytics. For user-friendly tools, we have Patient Explorer that was developed by Baker. It's a great cohort tool that goes through the structured data. We have Immerse that was actually brought in by CTSI, and it's used to explore notes. We're exploring new tools all the time. We saw a great demo from Vanderbilt the other day of a tool that they had that goes and really does chart abstraction from notes using LLMs. And lastly, there's Versa. I think there's been a lot of talk. Probably most people know about Versa. But again, the APIs going against Versa has been a huge thing of how researchers have been using Versa on the research side. Lastly, our roadmap here, you can see on the data side, we're doing things both to improve our data and make it quicker to bring in new data types, as well as bringing in some new clinical data types. On the tool side, you can see almost everything we're doing is AI-based. And that's because we're trying to lower the bar for researchers, for more and more people can use AI in their research in an easier way. And you can see some of the things we're doing there. Last slide. I think the important thing on here is attend the poster session this afternoon and to learn more and ask questions. Thank you.
Thank you, Rick, for our closing keynote. Thanks to all the fantastic speakers. It was a wonderful day, a wonderful amount of energy and engagement with the topic and with the promise. And if you were at the population health one, maybe you think it's peril, promise, peril, both. But we're going to charge ahead. I want to make a special thank you also to Marilyn Ritchie, who's come all the way from Philadelphia to be our invited keynote. And I want to thank also Beth Berean and Angela Riss-Jackson. Where's Angela? Right there. They really did an amazing job. So please, a round of applause for them. There is, of course, another Slido. So please go to Slido, pound UCSF, and answer that question. As Chief Research Informatics Officer, I am from the Office of Research, which is in central UCSF leadership under Catherine Lucy, our Executive Vice Chancellor and Provost. So if you have thoughts and ideas, concerns about AI and how UCSF should move ahead institutionally, feel free to email us at crio@ucsf.edu. We've got a tremendous number of partners across the health system, across all our campuses, across the research enterprise, as you've heard today. We are all coordinated. It's an amazing group of people to work together. But ideas that you have that you want central leadership to know, we're very happy to hear about them. So I invite you now to go to our poster session, our networking, and our happy hour. As you know, there are over 70 posters. You've heard about some of them. So it's downstairs in the atrium. Enjoy yourself. And at the end, as you leave, please remember to recycle your badge. Let's be mindful of the environment. Thank you so much all for coming.